provide or any insights if you would like to provide, please don't hesitate. This is a very interactive session what we are looking at, and let's make it a grand success. Okay. So contents has been divided like this. About introduction to VLSI, where we'll be discussing on electronic circuit, followed by VLSI, and a history of VLSI, how VLSI came into picture, and when transistor was introduced, right? I mean, because everything begins with transistor in this VLSI field. But a lot of things we are going to cover. Then we'll go through the VLSI flow, right? I mean, different kind of flows are there. This will give us a fair amount of idea as from end to end, from beginning, right, from scratch onwards, how the VLSI flow is taken forward in variety of different methodologies, right? All of that has been covered into VLSI flow segment. Then we'll go into our main topic, right, for which we have assembled, that is physical design. What exactly is physical design, right? What we do there. And then we have picked up two nice demo labs, right? One is ArcaTop, which is the industry standard demo project given by Synopsys EDA vendor. We'll have a live demo there, where uh, Nilima and the team will be providing the demo there. And then similarly, another one is DTMF top, right? This is again another industry standard demo project given by Cadence EDA vendor. Here also we'll have a live demo. And then we'll touch base on the PD course content, what all things we go here in detail, the technical part, and then how it will equip you to have a 360 view of the physical design domain, and how in the end of the course, how you will be competent in applying to multiple jobs, right? I mean, what all things will equip you to enter into job market, right? And then we'll spend time on the question and answers, right? And then finally we'll wrap up with a summary note. Okay. So let's go to introduction to VLSI. All right. Let's go with electronic circuit. Okay. So electronic circuit. An electronic circuit consists of CPU, ROM, RAM, and other glue logic. So we all might be aware of central processing unit, read-only memory, right, RAM, and other glue logic, right? Now what happens is VLSI lets IC designers, IC means integrated circuits, IC designers add all of this into one chip. Okay, if you see on the right side, right, look at the VLSI chip here. It's so small that on your finger it is looking so small. Okay, this is the size of the chip, right? Now, a brief history on how VLSI came. Okay, so VLSI began in 1980s when complex semiconductor technology was being developed for integrating transistors, right? So semiconductor is the foundation for VLSI. Now, semiconductor technology was booming in 1980s, right? Almost 50, close to 50 years back, right? And because of booming of semiconductor industry, it helped us to integrate multiple transistors into a single chip, right? So I believe probably you might have seen chip in one or the other case, either in your mobile when you open your mobile back pocket, right? Along with battery, you will see a small chip on the top, or you might have seen chip either in your radio or laptop or TV, anywhere, right? Multiple electronic applications, right? Now, VLSI directly, the VLSI what we are seeing today, it did not come all of a sudden. So it went through several generations, right? The first generation was LSI, which we call it as large scale integration, then followed by medium scale integration and small scale integration. So these were different generations after which we are having VLSI, that is very large scale integration. Okay, we have crossed these three different stages: LSI, MSI, and SSI. Okay, Now, what is the definition? Basic, very simple, easy to understand definition of VLSI. Okay. So VLSI are very large scale integration. The full form of VLSI is very large scale integration. So it is a cutting edge process of crafting integrated circuits by integrating thousands, millions, or even billions of transistors onto a single silicon chip. So inside your chip, okay, by the way, this is a PCB board. You can look at the PCB board. If you open any electronic device, you can see this PCB board. And whatever the chip you are seeing, that is called as VLSA. Okay, where I'm marking with the laser pointer, right? Now, if you open this one, the meaning of this sentence is thousands or millions or billions of transistors are sitting inside, and they are working as per the functionality what is defined. Okay, because we have chips for different applications. It can be medical application, it can be automobile, right? Or it can be even two-wheeler, right? Everywhere, wherever we have microprocessor, microcontroller, or let's say in automobile, ADAS 2. Right now, the latest what we have is ADAS 2 in every four-wheeler vehicle, right? So that will help in assisting the driver for driving in a smooth way, right? ADAS 2 is the latest level what we have. So everything is controlled by this chip. It's something like the human brain, how the brain controls the human body. In the same way, the electronic product is controlled by the chip. Okay, by integrating thousands, millions, or even billions of transistors onto a single silicon chip. Now, this silicon is called as semiconductor. Okay, we need silicon in order to integrate thousands, millions, or even billions of transistors. This integration has to happen on the silicon substrate. So that is where we need this semiconductor as well to go hand in hand, right? Okay, these integrated circuits power everything from everyday gadgets to state-of-art supercomputers, right? VLSI design involves working with circuits at incredibly small scales to create high performance and compact electronics. Okay, supercomputers. I just want to spend a minute here, right? Supercomputers are the computers which can do lakhs together simulations in a very small amount of time. Okay, so hardly a half a day or 1 day time frame. They can do lakhs together of simulations. They can do permutation and combinations, right, of the inputs which you have given, and they can provide you which output is the best based on the inputs what you have given. So especially the pharma companies, they used these supercomputers during COVID in order to come up with a medicine which can cure the COVID, right? That's where the supercomputers were effectively used by pharma industries to come up with a drug that can cure COVID, right? Lot of applications, but recent application is COVID-related drug. Okay. Please halt me if you have any questions or any inputs. Okay. Now let's go into history of VLSI. As you can see on the top, right, this is one single transistor. Just look at how big it is. Okay, a single transistor which was invented in Bell Laboratory in 1940. Okay, so it is so big, one single transistor, right? This was in 1940. Then in 1950, right, I mean the integrated chip came into picture. Okay, that is nothing but JK flip-flop. Those who know about digital electronics, JK is like one of the flip-flop, right? And in 1960s, early 60s, small-scale integration, as I mentioned in my previous slide, right? I mean SSI followed by MSI, followed by LSI, and finally VLSI, right? So SSI means like 10 transistors on a chip, only 10 transistors, right? And then medium-scale integration means hundreds of transistors. Okay, and in 1970, right, so early 70s, large scale integration LSI, where like thousands of transistors on a chip. And in 1980, early 80s VLSI, right, 10,000 of transistors on a chip. Later it became 1 lakh and more than 1 lakh. Okay, and then 1989 ultra LSI is sometimes used for, I mean, like more than 1 crore transistors. Okay, So this is how the era went into, right? So this transistor invention followed by the development of semiconductor, right? Both went hand in hand in order to start integrating more and more transistors into semiconductor, right? That's how it goes. And based on how many transistors we are integrating, accordingly, it falls into either SSI bucket or MSI bucket or LSI bucket or VLSI bucket or ultra LSI bucket. Okay, but generally we use the terminology VLSI for n number of transistors going into integrated circuit. Okay. Yeah, this is interesting one. So let me read out a brief intro again, and then I will explain about this particular image which has been put here. It's a very interesting image. So the journey of VLSI design began in 1950s with the invention of the first transistor, as I mentioned, right? I mean, in the Bell laboratory. This breakthrough was followed in the 1960s by the development of the first integrated circuit, a milestone that transformed the electronics industry. The advent of ICs significantly shrank the size of electronic devices while vastly enhancing their capabilities. You can enhance their capabilities how? By a simple logic, by adding more and more transistors, right? The 1970s introduced the first microprocessor. Now everyone might have studied, right, during their graduation, what is microprocessor or what is microcontroller. So just to give a one-line difference between processor and controller is processor will process the inputs and provide you the output based on set of rules that are defined inside the processor. But microcontroller can also think on its own as which is best to process and which is not best to process, and accordingly it will decide the output, right? It has that thinking capability. That is the difference between microprocessor and microcontroller. Microcontroller is much advanced than microprocessor, right? Marking the dawn of the modern computing era. By the 1980s, VLSI design emerged as a specialized field, with the first VLSI chip being designed in 1983. Since then, the field has rapidly advanced, pushing the boundaries of chip complexity and efficiency. Now, on the right side, if you see, right, I mean, this is one hair particle. Okay, just one hair particle, human hair particle. Okay, human hair, just one hair. The diameter of one hair human particle is almost 75 micron meter. Okay, now somebody mentioned like they have worked on 180 nanometer and 16 nanometer, if I'm not wrong, right? I just have taken the 16 nanometer example. Now, in the diameter of one human hair, right, which is almost like 75 micron meter. Now, if we take transistors which are at 16 nanometer feature, then we can accommodate around 90,000 transistors. Isn't it interesting? 90,000 transistors could fit in on cross section in this much of space, right? In the diameter of a human hair at the 16 nanometer range. Nowadays, we are talking about 1.8 nanometer, right? 1.8 nanometer and then 3 nanometer, 2 nanometer, right? Now for 16 nanometer itself, we can fit in 90,000 transistors, right? This is how the VLSI industry is booming, okay? And the chips are reducing into smaller and smaller size, adding more and more complexity, okay? Any questions here? So far, is it clear, everyone?
Yes, sir.
All right. So let's look at this image, another interesting image, right? This is way back in, let's say around 10 years back, 10 or probably 12 years back, 12, 13 years back. Okay, if you see the SD card, right, in your mobile, if we want to add extra memory, right, we generally purchase SD card, right, and then insert into our mobile, right? Now SD card, previously the highest what we can see is 128 MB. Okay. Now if you look at the SD card as on today, right, see the size is still smaller compared to this, and then it is in GB, 128 GB gigabyte as compared to megabyte, right? So a lot of difference. I mean, you can add more and more memory into a very small SD card, right? So a lot of advancements are happening in the VLSI industry, right, to make our life easy. Okay. Now there is an interesting law, right? I mean, in VLSI, just like any field has certain founders who predict how the field will look like, right? Similarly, in VLSI, right, we have a scientist by name Moore, and then he has provided a observation which we call it as Moore's law. Okay, probably in our graduation in 6th semester, right? In VLSI course, we might have studied about Moore's law. So what does Moore's law says? So Moore's law is an observation that over the history of computing hardware, the number of transistors on integrated circuits doubles approximately every year, almost 18 months. Okay, what does it mean? For every 18 months, right, the number of transistors that are present in the integrated circuit will keep doubling. And how it can be doubled? By reducing the size of transistor. So that's how we can double the size of transistors present in an integrated circuit. Okay. Now we have crossed this law, right? It's not double. We are into triple or maybe 4 times, right? We are able to pump in the transistors in the same size of IC, or we can reduce the IC size as well. Okay. The law has been shown from 1970 all the way to 2030. Okay. So this is how the Moore's law goes. All right. Has anybody gone through the Moore's law in their 6th semester? Audience, those who are on the bridge. Is anybody aware of the Moore's law? Okay. Thank you, Rashid. All right. Let's go to next one. So now, uh, if we look at VLSI, right, entire time we are working in a software simulated tool, right? Now, what happens after we finish our work in the software simulated tool, right? Now, finally, the real product, how does the real product come out? So for the real product to come out, we have to send our final GDS2, right? The final software file from the software environment to something called Foundry. Okay. So the Foundry person will have something like this, which is called as wafer. Okay. And the small square shaped box, what we have here, right? This square shaped box, these are all called as integrated circuits. So within a wafer, a slice of wafer, you can see that so many integrated circuits are there. Okay. Now look at this image here. So I have taken one of the integrated circuit, roughly around 1.5 centimeter by 1.5 centimeter. We can have even smaller chips also. Now this integrated circuit will be packaged, okay, in order to avoid the direct connection with the integrated circuit. We generally cover it with a package, the black color package. Okay, the package will be having the legs, which we call it as pins. These pins will be used by the integrated circuit to communicate with the external world, right? If the IC is placed in the printed circuit board, in order to communicate with the board, right, either it can be signals from IC to board or from board to IC, we use the pins. Okay. Okay. So this is how the IC is coming out in real form finally. After we complete the design and then do physical design, implement the design, right, and finally to to get the IC out in our hand, we have to go to fabrication unit. Okay. Now let's look at different products, right? What we are using based on the VLSI chips. So everywhere VLSI is there. Okay. So processors, it can be central processing unit, digital signal processing, controllers, and then memory chips, RAM, ROM, EEPROM. Okay. And then analog, mobile application, audio, video processing, programmable, PLA, FPGA, embedded systems, which are used in cars, factories, network cards, system on chip. Okay. Now, how does all this reflect here? You can see a laptop, right? You can see mobile phone, right? Or you can see a video game, camera, right? Or this is another kind of video game, right? So many things, desktop, right? Supercomputers, okay? Or handheld devices, okay? Or any of the other SOCs. So many products, right? Day in, day out, so many products, right? Which we are using for our life, right? Everything is powered by VLSI chips. Okay. Now, amazingly, the original Bell Lab invention of the transistor. Now, how did this come up? Okay. All this started by the first transistor invention in Bell Labs. Okay. Amazing, the original Bell Lab invention of the transistor combined a decade later with the refining implementation of an integrated circuit continues to drive exponential economic gain. Now, if you have so many markets in your hand, let's say TV, laptop is one market, okay, camera section is another market, gaming is another market, okay, and then what else? So supercomputers are another market. These are all different markets, different consumers are there to purchase these products, okay. So that will obviously help in exponential economic gain. Now you might have understood a bit as like why VLSI market is so huge, right? Because n number of products are depending on VLSI chip, right? And obviously the overall economic gain through VLSI is huge, okay? In the form of both improved productivity and growth of new applications. Today, an integrated circuit can perform almost any electronic function on a piece of silicon less than a centimeter square, right? From a PC to a cell phone to a television to an internet router, the industry can conceive, design, and deliver that function in an extraordinarily cost-effective and convenient form, a single silicon IC, right? Every product here, right? I mean, some of the products which we have put up here, right? Every product here has a chip inside, has an integrated chip inside, okay? That integrated chip, based on the user inputs, it is providing the needed output as expected by the user, okay? The thought process inside this every product is done by that integrated circuit which is sitting inside this any of the products, okay? All right. So that's how much important an IC is. Okay. Now let's look at a brief on transistors. Right. We have been discussing the first transistor came in Bell Laboratory in 1940s. Right. And at the same time, right, the semiconductor industry was booming, and we were able to integrate transistors, multiple transistors into semiconductor substrate, silicon substrate. Right. Now you might be wondering what type of transistor it is, right? So mass integrated circuits. In 1970s, right, the processors usually had only NMOS transistors. Okay. So these transistors were inexpensive but consumes power when idle. Even when you are not using your chip, right? The power consumption will keep happening, right? But we cannot keep continuing with this kind of transistor because nowadays pretty much every electronic gadget is based out of battery, and we need the battery life to be more, and very less power consumption has to be done by the transistors in order to increase the battery life, right? Okay, so with that we had to think about how we can improve on the transistors. So from only NMOS transistors, we moved on to CMOS transistors. Okay. CMOS means complementary metal oxide semiconductor, which means it has both PMOS and CMOS, PMOS and NMOS both. Okay. Now, from 1980s to present, even today, right, we are using CMOS transistors for low idle power, which means it is able to take care of the disadvantage what NMOS transistors had, right? That is when the chip is not being used, right? Automatically it goes into power save mode, which will help to save your battery life. Okay. So this is how one of the example from Intel 1101 256-bit SRAM. You can just see how many CMOS transistors are there, right? And then Intel 4004 4-bit microprocessor, right? So, I mean, this is the packaged one where you can see the packaged legs. These are all the packaged legs to communicate with outside world. And this is your die, which is coming from the foundry, the previous slide what we saw, right? So many transistors and they are connected to each other, okay? And then this is one of the standard cell which is developed from the transistor, okay? It has a VDD bus and P-type transistor and N-type transistor. P-type and N-type are separated by diffusion spacing. And then finally, at the below, we have VSS bus. Okay. Any questions so far from everyone? Is it understandable? Maybe we can pause for a minute and take any questions so far.
Hello.
Yes, please. Yes. Somebody had a question? Okay. All right. Thank you, Vivek. All right. Then we'll move on to first computer. Okay. Now, this is almost right. I mean, more than a century old. Okay. 1832. 1832. If you can look at this first computer, right? I mean, the image in the image, it may look a bit small, but ideally it's the size of a room or bigger than a room. Okay. It has 25,000 mechanical parts. There is no electronics involved here, right? And the cost is pound 17,470, which is a huge cost in 1932, right? Now, the reason being there was no electronic devices involved here. It was purely based out of mechanical devices, right? And that too 25,000 parts. The reason being the semiconductor industry itself started into picture somewhere around the 1950s, right, or 1960s. And the first transistor itself came into picture around 1940 by Bell Laboratory, right? So before that, whatever supercomputers are like first computers of those generations, right, they were all based upon the mechanical parts. Okay. This is called as the baggage difference engine. Okay. Now let's look at another interesting one. So this is another thing in 1946, ENIAC. Okay, ENIAC means electronic numerical integration and calculation. Right. The first generation of modern electronics is thought to have begun in 1942 with the invention of electronic switches and miniature vacuum tubes. By 1946, a large-scale computing device based on these new inventions was developed. The computing device was known as Electronic Numerical Integration and Calculation, ENIAC. ENIAC could perform thousands of calculations per second and was used in many applications such as scientific research and weather predictions. Okay. If you look at the image, right, this entire thing, you can look at how many machines are there. This entire thing in this room from one angle, right? The photo was taken from one angle. This is nothing but your ENIAC, the first electronic computer. And you can see here, there is one person here at the corner, right, manually connecting some of the switches. There is one lady here connecting different switches, right? And then one more person is here. right? He is trying to connect a couple of wires from this device to this device. So the device cannot function on its own. Like we need people as well who can connect the devices appropriately with the wires. Okay, this was the situation, right, during 1946, right, just before our independence. Okay, isn't it interesting? Right, if we look at our background and the present day, right, I mean lot of improvements have happened, lot of changes, right, a tremendous boost has happened in the VLSI segment, right. Now, yeah, this is one more interesting thing. Okay, so I have taken till 250 nanometer. 0.25 micron is 250 nanometer. Somebody was saying like they have worked on 180 nanometer, right? So 250 is just one step next to 180 nanometer. Okay, now these are the different processors developed by Intel. Okay, now as you can see, this particular processor Intel 386, okay, between 1.5 micron and 1.0 micron, the same chip, okay, if you see here, shrink in size. See here how small it is in 1.0. Similarly, Intel 486 in 1.0, look at the size and look at the size in 0.8, and then look at the size in 0.6, so small, right? I mean, this is how drastically the technology is shrinking. Now, the advantage of this reduced size is your overall product size also will come down. The power consumption will come down. You can add more functionality, right? And it will be like a handheld device, right? You can easily carry it with you. Okay. Similarly, Pentium processor. Okay, Pentium processor 0.8 microns. If you look at the size, the same processor in 0.6, the same processor in 0.35, the same processor in 0.26. Look at the size shrink. Okay. Similarly, Pentium Pro and Pentium 2 processors. Okay. So in 0.6, 0.38, 0.25. Okay. I still remember my first laptop when I took it in 2004, I think, 4 or 5. Okay. During my MTech, I was using Pentium 2 processor, this particular processor. Okay, and with a limited memory. Now we have a lot of advancements here in terms of processors. Okay, this I have taken it from the Intel. The Cortex is from Intel, right? And you might be wondering, I mean, those who are not aware of what these numbers are, right? These numbers are nothing but manufacturing node. The above numbers 1.5, 1, 0.8, 0.6, 0.35, 0.25. We call this as manufacturing node. Okay, technology at a particular channel length, right? Okay, deep submicron technology 250 to 100 nanometer, nanometer technology 100 nanometer and below. All right. So this terminology is nothing but manufacturing node. So this is keep on decreasing. The manufacturing node is keep on decreasing, and it is allowing the VLSI engineer to incorporate more number of transistors, more and more number of transistors in a given integrated circuit. Okay. And also it is helping us to increase our performance as well. You might have seen Qualcomm Snapdragon advertisements in most of the platforms, right? In TV or in multiple multimedia advertisements and all, right? Qualcomm Snapdragon microprocessors and microcontrollers, right? I mean, the latest ICs which they have developed and which are being used in multiple mobile applications, right? So that's how the technology shrink helps us to develop more and more advanced integrated circuits. Okay. Now you might be having a question. Okay, this is all about technology, right? Now, how about companies? What are all the different companies that are working in VLSI? Okay, so we have just taken a top level view of leading companies, right? But the list goes endless, right? So many companies. Let's say IBM. IBM is one of the oldest company working in VLSI. Okay, and let's say Intel, right? Intel, everyone knows about Intel, right? I mean, Most of our laptops are powered by Intel, right? And then we have AMD. AMD is also competing well with Intel, right? And then what else? Uh, Broadcom is another important thing, and Motorola, right? I mean, especially those who have used their mobile phones, right? A couple of years back, probably 2011, 12, 13. That time, Motorola mobiles were I mean, they were tremendously famous. Everywhere we used to see Motorola, the flip phones, right? I mean, the flip phones were coming from Motorola. Texas Instruments, it is also one of the oldest company. Cisco, right? So many companies, right? I mean, the list goes on, right? Now let's move to, and Siemens. Siemens is also one of the noted companies in electronic gadgets. Okay, let's look at some of the VLSI foundries, right? So remember the previous slide where a person was holding the wafer, and from the wafer we saw an IC which is about 1.5 centimeters both width and height, right? And then it was having the package leads and all, right? Now we have a lot of foundries who develop the ICs. Okay. Now some of the main foundries are TSMC, right, which is located in Taiwan, and then we have Global Foundries, right, and then Tower Semiconductor, right. So many things. XFAB, right. These are all different foundries which will take your final software output, which we call technically as GDS2, and then they start converting into a real product, right? Which you can plug it into a board, and then from there into a product, electronic product, finally to have a electronic gadget. Okay. Now let's look at the EDA companies. So EDA companies, even today, right? I mean, the dominant EDA companies, right? Or we can say gorilla in the room, right? In EDA companies, the giant companies are, one is Cadence, right? Even today, for a majority of our projects, we still depend on Cadence EDA tools. Similarly, Mentor Graphics, and finally, Synopsys. These are the three main companies, right? And they are trying to uh, purchase the smaller EDA companies, right? That's how even today these three are the main EDA companies which are available for designing a VLSI chip. Okay, all right. So let's look at some of the VLSI design challenges. Okay, any questions so far? Anybody? All good so far?
EDA
And
means EDA.
EDA means EDA means electronic design automation. So it's a software similar to how you have MATLAB software, right? I believe majority colleges have MATLAB software. So, right, I mean the similar way for designing a chip, we need a software, right, where we can visually see the transistor, visually see the standard cell, visually see the net which is connecting between standard cell to standard cell, or from one transistor to another transistor. So to visually see and design the chip, we need a software. That software is called as electronic design automation. In VLSI, we call that software as EDA, electronic design automation. Make sense?
Okay.
Okay. All right. Anybody else? Any other questions from anybody? All good. All right. Then we'll go to some of the design challenges. Okay. So VLSI design challenges. So what challenges we may have, right? I mean, now things are going smooth. We are able to reduce the size of the chip, right? Because of technology node shrink, right? Now everything is looking good. Economy is rising. So many products are coming out of VLSI, right? Electronic gadgets, right? Variety of electronic gadgets, and there is no limitation to that, right? You are into uh, you are into various industries, okay, not just automotive, medical, consumer goods and all, but you are also into defense as well. Even the defense organizations from different countries, they also use VLSI to prepare the gadgets as needed by defense. Okay, so let's take a question from the bridge. Uh, what is Innovus? Right? Is that the question? Uh, is that right, Ramya? What is Innovus?
No, he's asking what about Innovus tool?
Innovus tool. Okay.
Yeah,
So
yeah.
Innovus is a EDA tool, is one of the EDA tool by a company called Cadence. So Innovus EDA tool is used for implementing physical design. So we'll be covering the Innovus as well in our PD course and in live demo session as well, along with the Synopsys ICC2 tool. Right? I mean, both are the similar kind of tools. Of course, Innovus is coming from Cadence, whereas ICC2 tool is coming from Synopsys. That's the difference. But both tools predominantly they are used for designing the physical design, implementing the physical design. All right. Does it answer your question? Shall I? Yes. Okay. Thank you, Kiran. Okay. All right. So let's come back to VLSI design challenges. Right now, what is the problem statement here? Designing circuits with increasing complexity in shorter time. Okay. This is the major challenge what we have. Okay. As the technology is booming, right, we are in need of more and more chips to come out, right? And that too in a short period of time. That is the requirement. Now, in order to provide the chips in a very short period of time, right, what should we do? We have to reduce our cycle time. From beginning till end, we should be able to implement our VLSI design in the very short span of time. Okay, in order to capture the market, we call this technically as time to market. Okay, we should be able to send our product to market as soon as possible. That is one of the biggest design challenge what we have. So computer has to take over routine work. Right now, how to come up with shorter times, right, in order to manufacture the chip. We can do this if we can utilize the existing computers to take care some of the routine works, so that the user is freed up and he can focus on other activities, right? Deliberate the designer from unnecessary low qualification work, which means some of the routine works or some of the works where we are already aware that, right, this is expected. So all those works can be given to the computer and the user can be freed up, right? So that way the user can focus on the design activities and help in reducing the cycle time, right? Shift of design activities to higher level abstract work, which means we can take advantage of the software languages in order to do some automation. Okay. Higher level abstract means we can take advantage of C language in VLSI, we can take advantage of system C in VLSI, right? So taking advantage of the languages what are available and then try to automate the flow to reduce the cycle time. Next, computer has to support new design methods. Now we are depending more on the computer, and whatever the computer we are choosing, right? This computer should be equipped to handle that kind of work. Okay, so these are some thoughts which go into in order to reduce the cycle time of designing the VLSI chips, which is our biggest design challenge, right? Okay. Now let's see how generally a chip is designed, right, from beginning till end. Okay, of course, the same time to market what we discussed in previous slide. Stronger market pressures. Okay, market is needing more and more electronic gadgets and with more features added, right? More features added, less power consumption, and in a small size. Okay, these are the three different requirements, right? Now market pressure is high and we need to release our chip as soon as possible to market. That is called as time to market. So decreasing design window, which means our design cycle has to be reduced, the design window has to be reduced if you want to quickly go into market, right? And then less tolerance for design revisions. If at all any mistake happens in the design, right, very less time is there for design revisions. Okay, we cannot take the risk of design revisions because it will hit our time to market, right? Exponentially more complex, greater design risk, greater variety, and a smaller design window. This is the summary. Okay. Now let's look at how the design cycle goes. Okay. Initially, very beginning, right? What does it take to design VLSI system? So very beginning, we need to come up with an idea what kind of chip you want to do, right? That's how any kind of chip work will start, right? I mean, we have to come up with what is needed by us through the electronic devices, what kind of chip we need, right? What is our end goal, right? What we want the chip to perform, right? We have to come up with an idea. That idea has to be crystal clear to make sure that whatever the next steps we are doing, right, that is all depending upon your idea, right? You need to come up with an idea what kind of chip you want to do, then convert that idea into something technical, right? Because we cannot take this idea forward unless you cannot map your idea technically. So second step is write specifications, where you are mapping your idea into specifications. Okay. And once you have some technical content here, right, specifications, then these top level, very top level specifications, right, where technically you have written down your idea, these specifications are mapped into design system. Okay. Now gradually we are going one step down and then going deep into technical aspect. It can be either digital or it can be either analog. Right now, as we know from engineering background, digital means always it shows us either 0 or 1. The output of digital logic will be either 0 or 1. Whereas if it is analog, then it is a continuous signal, right? Now we have to start bucketing down into whether it is analog or digital, and or if it is a mixed signal where we have to take combination of analog and digital. We have to go a little deeper from the specifications, right? Now this is the third step. From here, we need to start analyzing, right, how we can reduce the cycle time, right? Because previously we discussed what is the biggest challenge in VLSI even today, right? This has been the challenge over past decade as well, right? Is to reduce the cycle time, to quickly push the chip design, complete the chip, fabricate the chip, complete the chip, test it out, and then release it to market, right? That's how the challenge is, right? If we delay, right, the market cannot be captured, right? As per the market requirement, on time we should be able to deliver the chip to the market to capture the chip, right? Now, analyze model system, everything is related to that, right? We go again little deeper in from the third step, as where and all we can further optimize our implementation. And from here, if it is satisfactory, we start our design process. And once the design is completed, of course, physical design also is part of this fourth step. Okay. Now, once everything is completed, including physical design, it goes to fabrication, where we saw, right? I mean, one of the foundry person was taking out the IC from the wafer, right? 1.5 centimeter into 1.5 centimeter. So that's how the IC comes. And before we release the IC into market, we have to test and make sure it is working as expected. If it is not working, again, we have to go back, right? Go back, redo physical design, everything, and then take it forward. Now, previous slide also, as we discussed it, right? I mean, if we go back again, right, we don't have much time for iterations, right? Because if we keep iterating, we will lose the window, design window, and we cannot meet the time to market requirement. Okay. Now, this is on the very top level. Now, let's go a little bit deeper into each of these. Okay. Application or idea means what type of chip you want to do, right? Whether you want to do a processor or you want to do a chip for other application, or you want to do a SoC where multiple chips are connected, right? You need to have a clear idea what is exactly the outcome of the product you want to have, right? Okay. Now, once you have the idea, the second thing is map it down into technical specifications, right? To map it into technical specifications, right? So you need to have instruction set, interface, IO pins, organization of the system, functionality of each unit in the system, and how to communicate it to other units. Okay. So technically, mainly you are mapping the idea into technical requirements. That is nothing but your specifications. Okay. Now, third step is design and analysis, right? Design and analysis, where initially you are writing the design in VHDL or Verilog hardware description language, right? Just like C language, how we have, which is universal. Similarly, we have something called hardware description language in VLSI, where like either using VHDL or Verilog, you will code your design. Okay, you will code your requirement, then map this into gates using a process called synthesis. Okay, and these gates internally, these gates are made up of transistors. Okay, again the basic ones, right, which we discussed, right? CMOS transistors. And from here you will start having the layout, right? I mean, where like your physical design comes into picture, and from here these gates are routed, right? These connections, see here, X, Y, Z, these are the connections between G1 gate to G4, between G2 gate to G4, between G3 gate to G4. These connections are routed here, and finally we will have something like mask layout. This is the one which is sent to foundry for fabrication. Okay, based on the layout patterns, the foundry will start fabricating, and it will provide you the die which is packaged by the packaging unit. Okay, and that will be sent to market after it is tested, right? Now, if you see here from the mask layout patterns from the previous slide, the next step is to send it to foundry. Okay, and the foundry person will be having something like this. This is called as wafer slice, right? Using this wafer slice, the same one, right? 1.5 centimeter, 1.5 centimeter, and these are the pins which are related to package, because the package has to be used for packing this die so that the external damage does not happen if you touch the die. Okay, the package will be the external case protecting the die inside. And finally, you will have something like this. Okay, this is the chip. Okay, and this chip finally after packaging, it will be something like this. This is one of the example, Intel Core 2 Duo, and this will be put in your printed circuit board, right? Somebody mentioned their sister is working on the testing side, right? I mean, the testing happens on the printed circuit board to make sure that the chip is working fine in the printed circuit board, and that printed circuit board goes and sits inside the product. Okay, so this is how the fabrication comes into picture. And finally, before you send it to outside world, right, this Intel Core 2 Duo, this is just one example. This has to be tested, right? You might have seen some of the chips, right? I mean, tested, okay, they will put that symbol, right? What does it mean? We don't want to send any damaged chips to market, right? No matter how much pressure we have in VLSI to reduce the design cycle and send and design the chips as quick as possible by using the help of computer or by using the help of high level abstracts, right? Using the languages and all, right? No matter what, we have to make sure that any chip which is going to market has to be thoroughly tested. Okay, so that is where the sixth step comes into picture. Evaluate design and compare to model. See here, these waveforms has to come properly. These are called as sine waves. Okay, check signal integrity, power consumption, input output behavior. Does the chip function as it is supposed to be? Does it work at desired clock frequency? Right? Clock frequency is an interesting term. You might have seen again in the same Qualcomm Snapdragon advertisement, right? Which they keep posting in the TV ads and all, right? They keep mentioning about clock frequency. So the clock frequency is the one which will determine how fastly your chip can work. When you give any input to the chip, right, how quickly it can respond. All that depends upon your clock frequency. Now, before we release our chip into market, we need to make sure of all these things. It can be clock frequency, it can be functionality of the chip, it can be power consumption because we want our battery life to be more, it can be signal integrity, lot of things, whether the input and output are working fine, whether the chip is able to receive the input and deliver the output as expected. So many things go into picture. Okay. After all that is done, only then your chip will come into market. Okay, you can just imagine how many steps are going into. Okay, from the idea till the final step where you are testing and releasing the chip to market. In between, lot of steps are going into. Okay, now let's look at some of the design styles. Okay, now there are four different types of design styles. One is full custom. Full custom generally we refer to the analog logic. As I mentioned, like it is a continuous signal which we look at. Again, in analog, it can be, I mean, we can manufacture the chips which are related to signal. We can manufacture the chips which are related to power. Okay. So analog, it processes continuous signals such as temperature, sound, and light. We cannot digitize the temperature, sound, and light. It has to be continuous. Okay. Next, application-specific integrated circuits, ASIC, which falls into digital bucket, as you can see here, ASICs, okay, which is again part of digital. And then programmable logic, which we call it as PLD, FPGA, field programmable gate array, programmable logic design, right? So FPGAs are also falling into the digital bucket, okay? And then system on chip, that is nothing but SOCs. They are again falling in digital bucket. Now, if you see the digital, again in digital, you have memory and the logic. In logic, you have GPUs, graphical processor units, and then central processor units, okay? Again, you have ASICs, application specific integrated circuits, and then field programmable gate. Here you have under memories, DRAM, dynamic random access memory, NAND gates, and then you can combine majority of these into a very big complex chip that is nothing but system on chip, SOC. Combines other chips onto one chip, include memory, CPU, GPU, right? Combining majority of these smaller chips, right? You can make a very big chip that is SOC. Okay, this is possible nowadays because of not just because of reduction in the transistor size, but improvement in the semiconductor technology as well, right? Both have to go hand in hand. One is semiconductor technology, another one is transistor technology, right? Because of semiconductor technology, we are now able to meet the SOC requirements. Okay, all right. Now let's look at another interesting thing, intellectual property. What are intellectual property, right? We call this as IP, right? These are pre-designed components, may come from outside vendors, internal sources. IP saves time, design cost. IP blocks must be designed to be reused. Now, as we discussed, the biggest challenge in VLSI is the cycle time. We need to manufacture our chip as soon as possible and deliver it to market. But of course, in this process, we should not skip any step. All the steps are important and they have their own significance, right? Now, another way of speeding up this design cycle, right? Apart from using the computer, reducing the user work, apart from using high level abstract, all those things, we have another option called intellectual property, where some other vendors will prepare these intellectual property related reusable blocks, which we can directly license from the outside vendors or from internal sources. Internal sources means our own company is able to do the IP also. There is a separate team working on IP in our own company. That is called as internal source. Next to outside vendors means some other companies. Now we can license these IPs and directly plug it into our ASIC chip or FPGA chip or into SOC chip or into analog portion. Okay, that is the advantage of intellectual property, right? And again, in intellectual property, we have again two types. One is hard IP and another is soft IP. Hard IP means already everything is done. We just need to plug it in and then take it forward. We don't have to do any other things related to design work. Okay, it is pre-designed layout, allows more detailed characterization. Whereas soft IP means only the RTL is written in either VHDL or Verilog, and then from there onwards we have to do the remaining steps. There is no logic. Okay, there is no layout. Only we have to do logic synthesis, PNR, and then finally take the layout and then take it forward for integrating into chip. Okay, this is soft IP, right? IP layout is created by the IP user, right? These are the different types. Based on our schedule of the project, we have to decide whether we want to go for hard IP and soft IP. And obviously, since the layout is already done in the hard IP, the cost of hard IP will be more compared to the cost of soft IP. So based upon the cost, we need to decide which one to go, whether it is hard IP or soft IP, right? Now let's look at uh, another view of the design cycle. Okay, so this is again from spec to simulation, right? And then we have a little more details in this particular slide, right? So as usual, by taking the idea into specification, right? This specification is converted into VHDL code, VHDL behavioral model, and then we need to make sure through simulations that this behavioral model is meeting the specification requirement. And if at all simulations are passing, if at all the behavioral level simulations are passing, then we go for VHDL RTL, right? Where again we do simulations to make sure that these simulations are proper. And then from there, this is transferred into synthesis, where, right, we will have the netlist before layout. The netlist is generated. This netlist from synthesis is the input for place and route, right? And the place and route again internally has a lot of steps. Finally, we will be generating the netlist after layout. This is before layout, this is after layout. And here as well, we need to do the simulations to make sure that it is meeting the design specification. So everywhere we will be doing the simulations, right? To make sure that it is meeting the design specifications. Of course, nowadays to reduce the design cycle, right, we just do the simulation at the RTL level, and at the next stages we depend mostly on the formal verification. Okay, that is the easiest way to make sure that the design is intended as per the design specification. Okay, all right. Now this is another pictorial view of the design flow, which covers the logical design and the physical design, right? The logical design, as you can see, right? So it is covering till your floor plan part, design entry from the start, design entry, step number 1, step number 2, logic synthesis, step number 3, system partitioning, where we break the bigger logic into smaller portions, as you can see here on the right side, right? I mean, this smaller box is the box A, which we have shown here, right? These are all the smaller blocks out of the bigger top level design, right? This is called partitioning. And we go to pre-layout simulation. If it is passing, then we go to step number 5, floor plan. If it is not passing, then again we have to repeat 1, 2, 3 steps, right? So floor planning, placement, 6th step, 7th step routing, followed by extraction, where we extract the resistance and capacitance, right? We know about KCL and KC, Kirchhoff's current law and Kirchhoff's voltage law, KVL, right? So we do the extraction, identify the resistance and capacitance, and take it forward for simulations to have the parasitic based simulations. Okay. Now this particular portion, right, these are all the steps are falling in the physical design, and these steps, right, 1, 2, 3, 4, these steps are falling in the logical design, and floor plan may fall both in logical design as well as in physical design. That's how the pictorial image represents. Okay. All right. Now this is just another image where we are showing what is front end, what is back end. Okay. So front end, right, from the VLSI ASIC flow, right, the front end part. Okay, the front end covers design specification, behavioral description, RTL description, which is in HDL, It can be either VHDL or Verilog, then functional verification and testing, logic synthesis. These are all the front-end steps. The back-end steps are from here, the gate level netlist followed by logical verification and testing, floor planning and automatic place and route, physical layout, layout verification and implementation. This is all about back-end. So this is front-end steps, these are back-end steps. And from here we go to fabrication, that is fab. Okay. So we are just trying to highlight on the different terminologies what we generally use in VLSI. Okay. Now, what is exactly physical design? Now, with some introduction on VLSI, right? History of VLSI, what are the different IC products we can develop using VLSI, right? And what are the key VLSI design challenges we have? How many different types of flows we have, right? With a brief introduction of all that, right? Now let's try to understand what is physical design, right? Physical design or digital implementation is a process of importing a gate level netlist as well as the technology libraries and generating a physical design that meets power, performance, and area goals. Okay. We are taking the netlist as input, gate level netlist, and we are mapping it into layout. Okay. So Innovus is one of the physical design tool, right? I mean, sometime back somebody was asking about what is Innovus, right? So Innovus is the physical design tool. It looks something like this. Okay, it is the physical design tool which will map your netlist, the netlist which is present here, right? It will map your netlist into layout. Okay, the layout which is represented here. You can see here lot of standard cells are sitting inside, and these standard cells are routed. They are routed as per the connections defined here. Okay. So this process of mapping netlist into layout is called as digital implementation or physical design. Okay. And of course, it has a lot of steps. Partitioning, followed by floor planning and placement. If timing is okay, then we go for CTS and routing. These are all different steps again within physical design. And if routing complexity is okay, or if the compaction is okay, then we go for timing verification. And if timing is okay, then finally we go for fabrication. This is the flow chart what we can have. Okay, physical design flow chart. Okay, based on the yes and no conditions, we keep traversing whether to move forward or whether to repeat the same steps, right, in order to have the needed QR. All right. Now, these are some steps, right? I mean, how we proceed even in the cycle, entire cycle, from chip design specification to architectural design to behavioral and functional modeling to logic implementation, right? Followed by synthesis and testing, and then physical design and design layout. Now, this physical design is elaborated a bit here, right? So this physical design, as you can see, floor planning, placement stage, clock tree synthesis, routing, these are all 6, 7, 8, 9, right? And then final verification. All these things are done before finally we have design layout. That is nothing but GDS2. All right. Now, this is another view where in the entire cycle from the idea to the chip, right? So many steps are going on, and physical design comes here. Again, in physical design, we have so many steps here: partitioning, floor planning, placement, CTS, routing. And once the routing is done, we cannot directly send our final database of physical design to the next steps, okay, which are mask preparation, fabrication, and all. The final database of physical design, that is after routing, we have to make sure that the sign off is coming out clean. Without sign off coming out clean, we cannot take our routed database forward for mask preparation. Now, what are the sign off? Parasitic extraction, physical verification, formal verification, STA, static timing analysis, power analysis, IR drop analysis. Okay, only if these are passing, then we can take our routed database to the next step, that is mask preparation, followed by fabrication, packaging, and testing, and finally your finished chip to send it to market. Okay, so this is where we are, the physical design course, right, or the physical design what we are talking about. okay, in the entire cycle. All right. Now let's touch base on one of the reference project from Synopsys tools. Okay, the ARCA top. ARCA means optimized reconfigurable cell array. Okay, this is the reference design, right? Industry standard reference design which we use across the globe. Okay, even today, right? Where like we are implementing physical design using Synopsys tools. Okay, the ARCA top is a part of RISC processor, reduced instruction set computer, RISC processor. Okay, so it is a very complex design. It looks something like this in the physical design world. Okay, so this is the tool what we have, right, and which we use in our lab sessions. Okay, Synopsys ICC2. This design is nothing but ARCA top. These are the bigger cells what we have. The blue color ones, these are called as macros, and the other cells which are sitting here, right? These cells where I am moving my cursor, these are very small cells, right? These are called as standard cells. Okay, so we will be going through this session, right? Live demo session. Now, another important design, right, which we have from Cadence is DTMF, dual tone multi-frequency, DTMF. DTMF is a technology used with touch tone phones, best known to users as the sound made when pressing a number key, right? Even today we can hear the number key sound, right? That is nothing but DTMF, dual tone multi-frequency. It signals the phone company that you want to make a call and sends a command to the switch. DTMF is a reference project for implementing PD using Cadence tools. Okay. Now, if you see this particular image, right, it is from Innovus, right? This is the tool which we use in our lab work. Now, these are all the I/O pads which are needed for communicating to the outside world. So this particular image is the full chip, right? Full chip which we see here, okay, having the I/O pads, right? And this is the tool, Innovus is the tool which we use for implementing this project. All right. So we'll be having the live demo sessions, right, by Mujahid and Nilima. So let me cover a brief about course content, right? Of course, Ramya has covered it, but I will just touch base briefly here. So as part of course content, right, along with using EDA tools from Synopsys and Cadence, right? So we'll be going through introduction to VLSI, then we'll be going through digital design, followed by transistor level CMOS and FinFET. FinFET is the latest what we are using in 2024, right? And then complete ASIC flow chart, the different flows what we have seen. And then we will also be covering synthesis and DFT. In DFT, we will be covering scan insertion and stitching, right? And physical design deep dive, right? And then sign off checks. That is nothing but covering physical verification, DRC, LVS and antenna, STA and ECOs, right? LEC and formal verification, EMIR, UPF and CPF, right? Low power intent and checks. So 5 different types of sign off checks, followed by scripting. So again in scripting, we have different languages, Tcl, Perl, Python, right? I mean, somebody was saying they were good in Python language, right? And have written some scripts. So we'll be covering Python as well, Shell, Unix, and GVim. And apart from that, we also will be having 500 plus mock interview questions and answers. And we'll be also working on preparing the cover letter, covering all the technical details, and resume, again covering all the details. And then, of course, soft skills, right? As how to present yourself in interviews. Now, the PD course, right? The PD course content is designed to cover synthesis and partial DFT with respect to scan. Synthesis and partial DFT with respect to scan, right? And 5 different sign-off checks. These are the 5 different sign-off checks. 1, 2, 3, 4, 5. Physical verification, STA, LEC, EMIR, and UPF, right? With physical design in the center, right? With physical design in the center. Though the course is related to physical design, but we are also covering synthesis and DFT, which are before physical design, and we are covering the 5 different sign-off checks, which are after physical design, right? Now, how this will help each of us, right? This will extensively help to open up wide VLSI job opportunities for students, as now their domain's expertise is vast, right? So you saw the slides from Ramya, right, in the initial stage of the presentation, right? By the course curriculum is designed in such a way that since you are covering the before steps of physical design and also the after steps of physical design, along with covering the physical design, so your ground is more. The ground which you have covered is more. The expertise which you have gained in multiple domains is more, right? So that you can apply for multiple job openings in VLSA, not just the physical design, right? So that way the course content has been developed. Okay. And let me touch base on at the end of the course, right? What all things you will be equipped with, right? You will be experienced to handle designs for both RTL to GDS2. This is one big market what we have in VLSA job market. Another big market is netlist to GDS2, right? You will be experienced to work in either RTL to GDS2 or netlist to GDS2 in both the fields. Okay, gain hands-on in using both Synopsys and Cadence EDA tools, hands-on experience. Have thorough understanding of full ASIC SOC implementation flow steps. Geared up in between in below different domains. Synthesis, DFT for scan insertion and stitching, physical design deep dive for handling chip and blocks, right? You will be getting the chip level experience from the Cadence DTMF block, and then block level experience from the Arcatop block, which you are using from Synopsys. Then sign-off checks with respect to physical verification, STA, EMIR, LEC, UPF. Flow automation using scripting, right? Almost all the major languages are covered here. Equipped with 500 plus mock interview questions and answers, cover letter and resume, soft skills, right? And let me quickly touch base on what makes Semicon, right, different, because you have more than 500 plus mock interview questions and answers, right, along with preparing cover letter, resume, soft skills, then 18 plus years instructor-led training, right, self-paced learning when you need, wherever you need, right, and Synopsys and Cadence EDA tools, right, you have privilege to have both the tools, not just one tool vendor, right, both Synopsys and Cadence EDA tools, and weekly assignment tests and one-on-ones to track and make suitable adjustments to the progress of learning and mastering PD in VLSA. Okay, so these are all the different things. Okay, what makes Semicon different? Okay, any questions so far before we go to live demo of tools by Neelima and team? Why silicon? Why silicon
Is used more in the industry.
Uh, Ramya, can you? Okay, what is the question? Why silicon
Why
is more
silicon is
used
more used in the industry? Yeah.
industry?
Yeah.
Okay, so semiconductor industry is dependent on silicon because silicon is the one which will provide us to incorporate more and more transistors into chip. Because in the end, for a integrated circuit, in order to make it more compact, in order to include more and more design into silicon chip, right, into integrated circuit, right, at the bottom level we need silicon substrate. The material has to be silicon because silicon works as semiconductor, right? Semiconductor means what? You have insulator, conductor and semiconductor, right? Semiconductor is able to transfer the current neither more nor less, as appropriate. Insulator means it will never allow the current, whereas conductor means it will continuously keep allowing the current, right? So semiconductor is in between, and the properties expected from semiconductor in order to manufacture a integrated circuit, those properties are exactly found in the silicon. Silicon is nothing but your sand, fine sand, right? From the fine sand we prepare the silicon. Okay, One of the other reason is we can get silicon through sand. Correct, correct. That's exactly right. Through sand by purification process with it's more expensive actually. Silicon is more expensive. Yeah. So that's where we are striving to reduce the silicon cost as much as possible. So that's where the technology node helps us to reduce the size of the chip, which will help us to reduce the usage of silicon, which is nothing but the fine sand, right? Makes sense, Kaushik? Compared to germanium, it's a bit less expensive, I guess. Yes, sir. Okay. Yeah. All right. Nice. Yeah, nice questions. Thank you. All right, let's go to Tawfiq and Nilma.
Yeah. Okay. Thank you,
Thanks,
Casey.
Casey.
Thank you very much. So just
Thank you.
let me take a minute to introduce Nilima and Mujahid, who will be doing the demo session. I mean, like lab demonstration. So Mrs. Nilima is having around 18 years of experience in physical design, and currently she is working as a technical director at Radiant Semiconductors, which is a rapidly growing service-based company based in Bangalore, and it has its footprints now in US as well as in Hyderabad also. This is a brief intro about Nilima, Mrs. Nilima. And coming to Mujahid, Mujahid is also employee of Radiant Semiconductors. He's having around 5 years of experience in physical design, and currently he's working with our client Samsung. Thank you very much, both of you, for joining us today. Please go ahead. Over to Nilima and
Yeah.
Mujahid.
Yeah. Thank you, Ramya. Thank you for the brief introduction. So, hi, team. A very good afternoon to all of you. Hope you had a very good knowledge session on this VLSI and the entire cycle of VLSI and where RPD stands. Hope you had a good idea and briefing like where the PD stands in VLSI. So going forward, so whatever the designing we are doing, whatever the chip we are designing, or whatever the technical terms you have heard, right? So all should be implemented physically. So it can be any industry, it can be your automobile industry, or it can be anything, whatever is there. To implement all these things, we need some simulation or a simulator or some any tool where you have to work on that. So similarly, like we have the tools in AutoCAD for designing and all, same thing in the PTVLSI, we have different tools. So we have EDA tools provided by the top competitors. One is Synopsys and another is Cadence. Okay, so we have these two competitors who are providing tools for working on PD. So can we show the slide where we have the tools? Mujahid, you have it? Or Casey, can you show me the
Yes.
slide?
Yeah.
Yeah, yeah. Yeah, Mujahid, you can go ahead.
Yeah. Just give me a minute.
Yeah, yeah, sure. So we have two different competitor company tools. So mostly we are providing both the tools. One is Synopsys tools. So in Synopsys we have, like already Casey has mentioned, right? We have the different sections like synthesis, PNR, and sign off. So when it comes to synthesis part, we have Synopsys tool, DC compiler, and DC NXT. And for the PNR flow, we have Synopsys ICC tool. And for timing, we have PT, which is prime time. So these are the major tools which we have in the lab. So like as soon as you complete your sessions, like your theoretical sessions, you have to try to map it physically, and you need to understand the concept. So you have the lab sessions. So lab session, as you complete your theoretical part, you will have the lab session. So you will be working on these tools. So any one of you have some idea about these tools, or it's the first time you are hearing this? Did you ever heard? So what all different tools you worked in your BTech or MTech semesters? I think VHDL is one language you used. Any simulators or encoders you have used? Any tools in your BTech or during your academics? No? No one has used? Yes? No? I'm not hearing any answers. It's the first time. Oh, great! It's the first time you're in. So these are the major company standard tools, right? Whichever your companies or your real time, they use these. These are the industry standard tools. Synopsys. This is the company which is providing, and another counter company for Synopsys is Cadence. So both these tools are like they are the competitors in the market. So we are providing both the tools. So you'll have hands-on and lab sessions all on this both the tools. So coming to Cadence for synthesis, like similarly we have two different companies, right, where Synopsys is giving us DC. For Cadence we have Genus, and for PNR Synopsys is ICC2. When it comes to Cadence we have Innovus. So someone was asking what was Innovus in the previous session, right? Like this is the name of the tool which we use. Okay, this is provided by Cadence. Then coming to the timing, which is STA. Prime time is for Synopsys, and Cadence we use Tempest. So I'll quickly walk through the tools which we have. Mujahid, can you walk through the tools? Over to you. Can you walk through?
Yes, just a minute. I'll be sharing.
Yeah, take your time, no issues. So these are the major tools you'll be working on. So once you get into the course, once you get into the concepts, once you start using that, you'll get familiar to this. These are the two tools which are in the market currently. In overall complete market, overall the world, only these tools have been used majorly. Yeah. So if you see, this is Synopsys ICC2. ICC2 means IC compiler 2. So you can see the heading over, say it says IC compiler 2. I have already loaded a design inside that. So previously in the previous slides you would have seen how a chip was looking, right? So it was a screenshot, but in the tool you can see the chip like this. So you can see like there are different things in the chips. You can see some are colored in pink, some are colored in green color, some are like boxes. So these are the different things which are involved in the chip. So whenever you see a small VLSI small chip, so these are the things like transistors you heard, flip-flops you heard about macros, you heard about IPs. So all these 1 crore or 1 billion, 1 trillion, all these single transistors are embedded in this single block. You can see that as much as you zoom it, right, you can see the pink color small are your transistors. They are mostly called as standard cells. We say them as standard cells. So you can see them. There are many standard cells in our design. So this is one of the Orca top design which I'm currently showing you right now. So you can see that the Mujahid is going making it see and each and every standard cell. So if you see, you can see the layers inside that. Okay, to connect between the cells, we have something called layers, like simple like a wire connections. So you can enable them, disable them. So this is overall a chip or a block, a small part of the chip look like this. So you will have number of wire connections. You can enable them, disable them. So this is the place, like whatever the concepts you have learned. So everything, whatever theoretically you are learned, will be implemented practically inside this ICC2 tool. Okay. Mujahid, do you want to add something to that?
Yes. Yeah. Hello, everyone. This is Mujahid. Yeah, as you have seen here, this is a block level implementation. And as KC sir and Nilima ma'am said, we will be using our Synopsys and Cadence tools here. Like coming to Synopsys, we have for synthesis, we have design compiler. And of design compiler, just give me a minute, I'll be showing it to you. Yes. So this is the graphical user interface of design compiler. And here we have loaded one design, a netlist, and this is the schematic of that netlist, the design which we will be like working on. So later on, you will be seeing many more aspects while you'll be working. And coming to PNR flow, like we will be using ICC2 from Synopsys vendor, and this is the block level implementation which you are seeing there. And coming to timing analysis, as as you have seen this entire session, like coming to VLSI designs, like these days, like the complexity have been increased and not at a cost of lower performance, right? So we need a performance of designs to be high end, and that is the reason we are seeing like high frequencies. You might have seen 2.7 gigahertz, 3.5 gigahertz. Like the more the frequency, the people like more performance. So in order to meet those requirements, we will be doing timing analysis where we will be fixing all the violations, fixing the timing paths using prime time. And here I have just highlighted a schematic of a timing path. Later you will be learning more about this. And yeah, finally, like this is the overview of Synopsys tools. Yeah, yes, ma'am. This is the thing I would like to add. Yeah.
Yeah, thank you, Mujahid. So these are the tools we'll be working on. So these tools will be available like 24/7. Like you'll be given access and you'll given be plenty of the time to work on this. So like as much as theoretical you learn, the same practice has to be done even practically as well. So daily you'll be having some assignments. So we will be like giving you some lab sessions and you are given some assignments, and we will be there like 24/7. We have our technical support like virtually it is available, or directly also we are available. So you make once you are into this course, like you will have both access for both the tools as well as Innovas as well as ICC2. So look, this is the complete demo we are presenting to you. So any questions you have from the group? No, I guess. Okay. Yeah. Thank you, everyone.
Yeah, yeah. I would like to add one or two points here. Is with
Yeah, Mujahid.
consent. Yeah. So as Casey sir said, like this about this industry, this is evergreen and ever evolving industry. Like first of all, congratulations to all of you who have decided to know about this industry in the first case. And if you're willing to join with us, welcome. Actually, like in this generation, like we are seeing lot of technology, like let us say artificial intelligence, like which is emerging technology and which is going to be like ruling the technical industry in a very few years. Like already it is being implemented, and in very few years we can see a drastic change in the technology which we are using with AI. Like this, with AI, we need like high performance chips to support this AI as well. Like what I am supposed to say is this industry, this VLSI industry, like like all the technical industries are dependent on this VLSI, and like whoever like is joining this industry at this stage, I believe that it's a great choice, and like you'll see a lot of thing to learn here, and you'll grow like anything. Like you'll be in high demand like once you enter this industry and learn these things. So like yeah, all of you, like congratulations and welcome to this industry. Yeah, thank you for this opportunity.
Thank you, Mujahid. Just to add to Mujahid, right? So, a very recent 2024 financial survey of VLSI with respect to artificial intelligence and machine learning, right? This is again with respect to VLSI. So, 400 trillion is the projection. 400 trillion, not million, not billion, but trillion. And as on date, in VLSI, with respect to artificial intelligence and machine learning, we are able to take care only of 3 trillion. That's all. So we still have 397 trillion of business to take care. I mean, that much is the scope right now. And for that to happen, we need more and more skilled VLSI engineers, especially in the challenging fields like physical design, right? Where you are designing a chip, right? It can be digital, analog, mixed signal, right? So many varieties of chips, or it can be ASIC, or it can be SOC, right? Even FPGA, right? So that is how the business is. And this projection will at least take another 10 to 15 years or 20 years to at least reach 50% of the projected value. right? At least to reach 200 trillion out of 400 trillion projection. So this is how the market is. And just let me give one more example. So when COVID came, right, all of a sudden, which nobody expected in 2020, 2019 end or 2020, everyone thought it is end of world, at least end of electronics. Being in VLSI, we all were in dilemma, right? I mean, big companies were scratching their head as like, what will be our future? Okay, so much of investment is going on, and then it can be government projects, it can be private projects, right? What will happen to VLSA industry, right? Being in VLSA field, is it end of the world? No, right? That gave opportunity to develop gaming related things, right? Because we were all locked down at home, right? There was no scope to go outside because of COVID restrictions, right? It opened up opportunity to develop the chips with respect to gaming, right? Trust me, the companies which are working, which were working, and even today which are working in gaming division, right, they made tremendous amount of profits during the COVID time, and that led to invention of so many new gaming things, right? Those who are interested in gaming, right, I mean Super Mario, Nintendo Switch, right, so many gaming devices are there, right? The business in gaming increased multiple folds during COVID time. So, I mean, every opportunity, right, which comes in our way, it has a new dimension to look at, right? So with this, right, I mean, any more questions or any info, definitely we are willing to stay for some more time and then address and share some of the insights in VLSI, right? Or any inputs if somebody wants to share their own experience, right, based on their info what they have, please do share in this form. We can spend a few more minutes here on the Q&A, and then we can go for the summary part. Anyone? I mean, somebody was saying about developing a nice algorithm, right, which will reuse the power dissipation inside the chip, right? It was a new kind of algorithm, right? And Cadence Virtuoso tool was being used, I think from Davangiri, right? Okay, and other person was sharing about final year project done in machine learning. We can spend a minute or so if any questions or any inputs, right? We are happy to share as much information as possible because we want you to take home the info, right? I mean, take home what is happening in VLSA, what is happening in physical design as on 2024. We want all of you to be benefited, right, with the knowledge what we can share in this session. All right, seems okay. Let's take up this question. Sir, you said SI is more available and GE is less, but design goal is power, area, and performance. When these conditions, GE is less temperature, power consumption is also less compared to silicon. That is true. So there are chips where we do germanium based substrate as well, right? We choose the process based on the requirement, right? It is rightly said, Sai. Okay, so we have silicon germanium, or only germanium is there, silicon is there. Again, different type of transistors are there. Not just CMOS, but we also have bipolar transistors. Okay, FinFETs are also there, which are latest in the industry in 2024. Are we going to work completely on backend? That is true. So you will be primarily focused on physical design, but then as I mentioned, in the course content in Semicon is designed in such a way that you are also equipped with before steps of physical design, that is synthesis and DFT, and also you are equipped with the after steps of physical design, that is sign-off flows, 5 different types of sign-off flows. So physical design before and physical design after in the entire ASIC flow chart, you will be equipped with that along with lab works, as Mujahid and Nilima mentioned, right? I mean, you will also be equipped with equally the lab works as well, so that you have hands-on experience and you are equipped to either enter into different job zone, not just physical design. You can enter into synthesis, or you can make your career in any of the sign of 5 different sign of things which you are learning apart from physical design. So your scope of job, the range of job, right, job market, right, that will increase because now you are expert in different domains. And apart from that, you are also skilled in scripting, which you can utilize for flow automation. Did I answer your question, Kaushik V? Okay, thank you. Any other questions? Happy to take your questions and answer, because the whole agenda is to make you understand about VLSI, understand about physical design, understand about the course what we are offering, right, and how you can get benefited, right, by utilizing this course. Any more questions? We can have a minute, and then we can have the summary, final summary. Each chip should meet the each chip should meet low power, high performance, less area. I think SI is good option compared to any other at this moment. Silicon, yeah. As I mentioned, silicon, germanium, right? Based on the chip, we try to take up the suitable substrate, which is suitable for our design requirement. Is it required to get high-end laptops to install tools? No, no, you don't have to worry about it, because we generally provide it to provide the lab work through VPN. So what happens is, if you provide it through VPN, then what happens is you don't have to worry about having high-end laptops. Okay, so VPN will take care of the server related requirements. All right, makes sense, Farooq and Kaushik? I am a electrical department student currently studying third year. Can I learn VLSI? Absolutely, absolutely. Yes, Sravanti, absolutely.
Casey, I just want to add one thing.
Yeah.
During the questions and during the inquiries, right? Most of these students will be asking me, we are not from ECE or else triple background. Still, we will be able to take this course. Means like, as they doesn't know much about the digital electronics, so they're like asking, after completing this course, as we teach from the basics, will be they able to cope up and get into the industry? Yeah, that is the question.
That is true. So we can definitely cope up. The students from electrical industry, computer science industry, IT industry, right, or from the respective BTech backgrounds or MTech backgrounds, those who are into electrical, computer science, IT, right, they can definitely get themselves benefited from this course, because we will be going from scratch, as Ramya mentioned, right? So the main intent of semicon, right, the way we teach physical design or any other courses for that matter, right, we go from scratch, right? No matter whether you are from electronics and communication background or from other domains, relevant domains, we go from scratch so that everything will be covered, right? By the end of the course, you will have basic level to advanced level topics covered, along with the hands-on tool expertise, and with added advantage of scripting to compete in this market. Okay, so that's absolutely fine. Radiant projects are taught here for training purpose. Yeah. So we do have projects given by EDA vendors, as we mentioned, right? ARCA top and DTMF top. These are the standard industry projects given by EDA vendors. And we make sure that these standard projects are being used for the training purpose, right? Which are acceptable all over the world, all over the globe, right? As industry standard projects. Okay.
Yeah, based on the question of Ritvik, I just want to add one point. You asked that are we collaborated with Radiant Semiconductors? See, Radiant Semiconductor, I mean, Semicon is a sister concern company of Radiant Semiconductors. We both, I mean, like both Radiant and Semicon work independently. We do not take the projects of Radiant and give it at Semicon. Semicon is a different entity, but we are both collaborated. That's the reason. You get the placement assistance basically at Radiant Semiconductors.
All right. Yeah, these are all the wonderful questions, right? All right. Now let's slightly move to the wrap up part, right? Of course, it's getting closer to lunch time, right? Slowly, let's get into wrap up part, summary part. Okay. So any kind of such questions, right? Such wonderful questions, right? Which we are posting in the chat box, right? So please get in touch with us, right? You can visit our website semicontext.com, or you can also connect with Ramya and you can share your insights, right? You can write to us at info@semicontext.com. Okay, and we'll be happy to take all your questions, right? And then provide as maximum clarity in answers as possible, right? So that you get the needed info. All right. And with this, I would like to thank each and everyone, right, from Semicon for participating actively in this session and making it a successful event, right? And a special thanks to Ramya, Kirti, and whoever is involved, right? I mean, in making and getting this PD demo session up and running. And then Mujahid and Nilima for providing the demo sessions, and whoever is involved directly or indirectly for making this PD demo session a grand success today. All right.
Yeah,
Uh,
thank you, Casey. Thank you very much for joining this session and giving such an informative and engaging. Almost it went for 1.5 hours. Thank you very much, and also thank you, Mujahid, as well as Neelima for this. This is for the audience specially. So Mujahid, Neelima, and Casey will be heading all the training sessions of Semicon Technolabs. I mean the physical design training sessions. They'll be handling the sessions. And also, if you have any questions related to the training program, like what is the fee structure, or else for how many, what is the duration, and all that, I have kept our contact numbers on the chat box. Please reach us, so we will help you out. Mujahid, you are about to say something?
Yes, just an add-on to the like the discussion which we had, like regarding people were asking like silicon and germanium comparison between them. Like as in your graduation also you might have heard like silicon is more preferred as semiconductor material compared to germanium. Like we know what is the nature of semiconductor when it comes to conductivity. Conductivity is between insulator and conductor. Like if our main motto is to just conduct electricity, we might have opted conductors. But here silicon, why it is better semiconductor than germanium is like its band gap between like valence band and conduction band, it is more than germanium. And one more thing is tolerance to temperature is more for silicon. Like at high temperature, like high degree Celsius, silicon will not be withstandable. Silicon chips will be withstandable. And one more thing is coming to power performance area, which was highlighted by one of the member. Like germanium will have more free electrons at room temperature than silicon, which might cause one of the leakage power issue compared to more compared to the silicon. Like like both are the semiconductors, but like when it comes to high end like or more preference point of view, silicon like based on these things, silicon is most preferred. Like there are many more things we can discuss later in the semiconductors module. Yeah, just to give an add on. Yeah, thank you.
Okay, thank you, Mujahid. There are some questions like, can I join if I'm in third year? See, it is preferable if you're joining in the final year, because in the final year you will be having only the project sessions. so that you will have time for this training. But if you're joining you in your third year or something, third year you will be having around 5 papers theory as well as 4 practical sessions or something. So it will not be possible. Like you cannot manage your training sessions as well as your college. So it is preferable for final year students. Yeah. And apart from that, if you're based in Chennai or anywhere, as we conduct these sessions both online and offline, you can take online sessions. Uh, can you tell about the timing and schedule? The timing and schedule we can promise only once we start the session, because the different kind of people will join the sessions, like few working class and few will be the students. So we will try to tailor the sessions based on the availability of the students as well as the trainers. But it's kind of you should be available whole day, because half day will be theoretical sessions going on and half day it will be practical sessions going on, so that if you give your full time for next 4 months, your placement becomes easy. So I think I have answered almost every question. Like there is one more question, night session. So that's what I'm telling. Uh, we will decide on the timing once we start the batch. I mean, before starting the batch, we can commit on the timing. And also, there's a one more question regarding the recording session. So all these sessions will be recorded, and when you're absent to any class or something, definitely we will give the access for the recorded sessions. You can just cope up with the missed classes. So pay after placement, sorry, this is not possible. Everyone has to do it before only. This is not basically only for placement. Yeah, fee structure and all this, you can contact the HR team after the session. You have the installment option, like you can pay it in 2 installments. The fee can be paid in 2 installments. Any other questions? So if you don't have any other questions, we can wrap up, I guess.
One more, Ramya.
Yeah, sure.
Join date for offline classes.
So we will be starting the sessions after 15 days. So usual process it is, after finishing the demo session, we will be starting after 15 days. So it could be mid of September. So location details in Hyderabad, it will be in and around the Kondapur area. We will share you all the, I mean, location details also. Past placement record and average salary. So if you, the placement salaries will be like, it will be starting from 3.5 lakhs in the service based companies, and the product based companies, it will be starting from around 7 lakhs. And also, see, most of the will be asking specifically about the placement. I just want to add one point. See, this we will give the placement assistance. Thing is, rest all is in your hands. I mean, we give the best quality training. You have to prepare well, and we will be giving you different channels for placements. At the end of the day, it is you have to clear the interview and get placed. So the past placement record, I can say almost it's 100% placement. If you see in our previous batch, like previous batch, there were around 15 students. Almost 11 students were placed in the semiconductor industry, but few 3 members or something like that, they themselves again shifted to the IT. They went for IT testing. So our batch size, it will be ranging between 20 to 25 members, not more than that. So if we have more than 25 members in each batch, we will be splitting them as 2 batches so that it will be easy for one-on-one training kind of. If online training, then how will be hands-on experience with tools?
Coming to the tools part, like you are not using any hardware tools here. Like everything will, as Casey sir mentioned, and Nilma ma'am mentioned, they are EDA tools. Like they can be installed. Like we will be giving you access to the VNCs. There you can log in, and you can get access to your lab tools, like in your personal PCs. So it is not a big deal. Like there are already in previous batches also, we are having online students who are comfortably and smoothly working on labs.
Do you have tie-up with Tata Semiconductor industry? As of now, no. If less than 60% and 3 year, what issue will be faced? What does it mean? See, that I understood 60% overall aggregate. Usually, few of the companies will be very specific with regard to the percentage what you get in your engineering. They are specifically taking only people who have more than 60%. But there are also few companies who will be taking if you have the percentage less than 60 also. I didn't understand the next one. And 3 year, what issue will be faced? You mean to say that you have a 3 year gap after engineering? If that is the case, it's not a problem. Gap is not a problem.
And yeah,
Jay, they wanted to say something.
no, sir, you answered that question. Like someone posted why MOSFET is preferred when compared to JFET.
Yeah.
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 So it has like one more thing is better performance is attained with MOSFET. Like higher switching frequencies will be there, as like we have metal oxide semiconductor there. So that is also one more add-on there compared to JFET.
That's all right. I think all the questions are done. So, guys, thank you very much for joining this session. And I want to add one more thing. Like most of you will be searching for the job. I mean, like from past 1 year or something, because of the poor market conditions, might be you're not able to grab it. But don't lose your hope or trust. Please stay in the same industry. I see many of the students like they'll be saying that we are not able to get into the VLSI industry, though we are so much interested. Uh, okay, but it's not like that. Definitely, you should wait. You should just have some patience. Definitely, you will have very good opportunities coming up, and you will be growing in your career. So you need just first 1 to 2 years of this thing will be like an experience, but later I assure that recruiters will be following all the VLSI engineers for offering the jobs. Yeah. So thank you very much. Thank you everyone for joining this session. Yeah, I think we'll be winding off. Okay.
Thank
Thank
you.
you. Have a nice
Thank you
weekend.
so much.